speaker is Raúl Oset Sinha from Universidad de Valencia, Geometry of the Cuspidal Crosscut.
Okay, well, so should I speak here? Yeah. First of all, I would like to thank the organizers for giving me the opportunity to give a talk in this conference and of coming to Mexico. It is a pleasure and an honor always to be here in Mexico, and especially to celebrate Federico's birthday. I think the first time we met was in 2009 in Valencia 1, and now this is Valencia 5, so it's been a long time. And I think that the idea of these conferences of singularities in generic geometry was a very good idea. There are many singularities conferences, but having one specifically for generic geometry is very nice, and so that's what I'm going to talk about, generic geometry basically. And there's been a recent impulse in the generic geometry of singular surfaces. And so the program for my talk is the following. I will start with a motivation, why we want to study the cuspidal crosscup. Oh, I forgot to say the title of my talk. I'm going to talk about the geometry of the cuspidal crosscup, and this is a joint work with Kentaro Saji. Okay, so I will explain why we are interested in this cuspidal crosscup, and then I will say how we study in general generic geometry of singular surfaces. So in a way I will also go through some recent work of many different authors on generic geometry of singular surfaces, and then I will explain our approach. And there will be two parts to the talk. The first one is about geometric invariants, and the second one is on flat geometry, in particular contact with planes. Okay, so, well, as I was saying, there has been a recent impulse in the study of geometry of singular surfaces. For example, only for the crosscup, or the Whitney umbrella, I think there are about 12 or 13 papers in the last 6 or 7 years, only for the crosscup. And also around 7 or 8 for cuspidal edges, and many for frontals in general, or wavefronts in particular. So, first of all, what is a cuspidal crosscup? Most of you must know, but basically any parametrization which is A equivalent to this normal form over here is what we call a cuspidal crosscup. And here we have the picture. It's like a crosscup, but with the difference that there is a cuspidal edge over there. Okay? So, what is interesting about the cuspidal crosscup? It appears naturally in many aspects of differential geometry or of generic geometry and singularities. For example, it's a generic type of frontal singularity. I will explain what frontals are later on. But it is not a wavefront, a generic wavefront, okay? It also is a generic singularity of bicaustics, which is if you consider a one-parameter family of caustics and you consider the surface drawn by the cuspidal edges, that is a bicaustic, and we have the singularity as generic in this case. It also appears in a developable surface of a space curve at a point of zero torsion. And it is also a generic singularity in dynamical systems, for example, in problems related to relaxational equations, which Davidov probably knows much better than me. Good. So, how do we study the generic geometry, or at least what has been done in the past few years to study generic geometry of singular surfaces? One very important tool or goal is to have a generic normal form, which is invariant under diffeomorphisms in the source, but only isometries in the target, so that we respect the geometry. Okay? And this generic normal form has coefficients, and these coefficients give the necessary freedom to capture all the generic geometry we are interested in. Okay? So, for example, Janet West, in her thesis in 1995, she obtained this normal form for the crosscup. Okay, so you have the u, uv, and v squared, okay, because this is different to 0. And for example, this coefficient over here tells you whether the cross-cap is elliptic or hyperbolic or parabolic. Okay, so this is a normal form up to a certain order. This normal form in particular is more or less up to order 2. But for example, in this other example, that is the cuspidal edge, this normal form was obtained by Martins and Sagi, and they went up to order 3. So one could imagine, to have a good generic normal form, up to what order should I go? And from these two examples, we could imagine that it's the order of determinacy, because the cross-cap is two determined, this is 3 determined, but it is not so. Other examples of normal forms are a very recent one. Sagi has a preprint where he obtains a normal form for the swallowtail. He does it up to order 4. The paper is devoted to obtain this normal form. So this is something in principle not so easy. Okay? And this is propaganda. Both Sidney and me, we have a common PhD student who is Pedro Benedini, over here. I think he is over there. And he's giving a talk on Friday. So he's studying, in his thesis, he's studying singular surfaces in R4. And in particular, he has studied this singular surface in R4, which is very interesting because it projects to a cross-cap, but it also projects to a cuspidal edge. And he has a generic normal form for that. He'll tell you on Friday. Good. So besides having a generic normal form, it is important to define invariants which capture this generic geometry we might be interested in. These invariants are what? For example, remember we are considering singular surfaces. So we can consider invariants of regular surfaces and we'll see what happens in the limit, or take a limit towards the singular set. Okay? Or we can consider the curvatures or torsions of the singular set. For example, Martins and Nuño Ballestero, for a singular surface in R3, rank 1, they define a second fundamental form, and the image of the second fundamental form of the unit tangent vectors is a parabola in the normal plane. It is similar to the curvature ellipse in R4, but it is a parabola in R3. And this parabola can be degenerate. And in the case it is degenerate, the distance of the parabola to the point P, the center of the plane, is an invariant which they call the umbilic curvature. If you are interested in this type of invariants, Pedro on Friday will talk about a similar invariant, a generalization of this invariant for singular surfaces in R4. So you can also study the behavior of the invariants near singular sets to see whether it is bounded or unbounded. And then it is very interesting to express the invariants as functions of the coefficients of the normal forms. Okay? So some people that have been working on this kind of invariants, geometric invariants, are all these people you can see here. Of course, this list is not extensive. I'm sure I'm forgetting someone that must be around here, so I'm sorry about that. It's just some recent papers about all this. Okay, so on the other hand, we can also study flat geometry. What do we understand by flat geometry? Flat geometry is contact with flat objects. For example, an inflection point in a curve, in a plane curve, this is something captured by flat geometry. It is not captured by A equivalence, but it is captured by flat geometry with the order of contact with a tangent line. And this contact with flat objects can be described by singularities of height functions, or for orthogonal projections, or things like this. And since we are talking about singularities of functions or maps, this involves a classification process. And there you can do certain classifications of singularities and apply them to this context, which we will see at the end of the talk. So some recent works where they have applied classifications of singularities to this context are Bruce West, Díaz, Nuño Ballesteros, myself and Farid Tari, Wall, or Barajas, Sichaga, and Cavata. Good. So that was general. Now let's go back to the cuspidal crosscap. What is our approach? We want a generic normal form. and then geometric invariants, and then we want to study flat geometry. But what order should I go to get this generic normal form? Okay. The thing is that if you take a section through the origin, a generic section of the cuspidal crosscup, we obtain this, which you might recognize as a rhamphoid cusp. Okay? So a generic normal form must consider up to order 5 at least. If we want to capture this geometry, we need to go up to order 5. But this is in principle quite complicated to obtain this generic normal form up to order 5. So, well, here you have the section, and here you have this rhamphoid cusp. Okay. So, what do? We want to avoid having to obtain this normal form, but not lose too much on the geometry. So, we take a generic cuspidal edge, and we take a plane transversal to it. Okay? And we fold the cuspidal edge along the plane. And this will give us a cuspidal crosscup. So you have this cuspidal edge and the plane transversal to it, and when you fold it, you obtain this double point curve and the cuspidal edge over here. Okay? This was first noticed by Arnold, and it's been generalized by Sagi in another paper. Good, so this is what we are going to do. Of course, we are losing some geometry, and I will tell you later on what we are losing by doing this. But we have some advantages. First, that we don't need a generic normal form. Why? Because we can use the generic normal form of the cuspidal edge, which we already know. And second, we can relate the geometry of the cuspidal edge with the geometry of the cuspidal crosscup. Okay? So this will be interesting later on. Well, this is just the approach we chose to do. I mean, it's... Okay, so more precisely, so we take this normal form for the cuspidal edge. Okay, this is a normal form for frontals in general, but with certain conditions, you can find that this is a cuspidal edge. And we consider the fold map, which is given by this over here. Okay, and the reflecting hyperplane will just be z equals to 0. We have to assume that the x term here is different to 0, so that they are transversal. Okay? And we just fold it, so we get the third component and square it. This is just the composition of the cuspidal edge generic generic form with the fold. Okay? And well, we know the cuspidal edge, the cuspidal crosscup has certain objects which are worth studying, which are a cuspidal edge and a double point curve, and these two are transversal to each other. So the singular set, which is a cuspidal edge, is given by y equals 0, and we call sigma the image of this singular set. And basically, it's parametrized by this over here. And the osculating plane is just the plane orthogonal to this vector. Remember that all these are coefficients of the cuspidal edge, of the generic normal form of the cuspidal edge. And the double point curve, well, we just take two different points with the same image, and we can parameterize the double point curve in this way, which is an even curve, okay, only even degree terms. And we consider so let me draw something here. So we have the plane, and we have a curve, which we call D, which is the double point curve. Then we have F, and this takes me to a cuspidal edge. And the image of D is a curve here. Something like this. And we call it the till. And then we have G, which goes to my cuspidal crosscup. I'm very bad drawing, I'm sorry, that's terrible, but that's the cuspidal crosscup. So we have D, we have D tilde, and we have here D hat. Okay? Let's remember those differences, because the idea that we are going to relate some geometry of this curve with geometry of the cuspidal crosscup. Okay, so, well, this is just some calculations, but the thing is that this curve, well, d tilde is a singular curve, and so is, oops, d hat. Okay, so, but we can consider, yes?
D hat is now the line of the double?
Yes, the double point curve. The picture is bad, I'm sorry. Yeah. Yeah. Okay, so the thing is it's a singular curve, but the second derivative vector product, the fourth, is different to 0. So we can consider the tangent vector of this curve to be the second derivative and the osculating plane generated by second and fourth. Okay. Good. And besides that, we also have a tangent cone, which is given by the plane z equals 0. Okay, so remember we were folding along the plane z equals 0. That will be the tangent cone. So that means that the cuspidal edge is tangent to that plane, and the double point curve is also tangent to that plane. Okay, so now let me just briefly mention what a frontal is. We have a map from R2 to R3. It is a frontal if there is a well-defined unit normal vector field along F. Okay? And it is a wavefront if this pair here is an immersion. In our case, the cuspidal crosscap is not a wavefront because that is not an immersion. So if we consider this function, lambda is the determinant of the partial derivatives and the normal. The singular set is the pre-image of 0 by this function. We call a singular point non-degenerate if the differential is different to 0, and at a non-degenerate point there is a well-defined vector field such that this is 0. Okay, so we call this a null vector field, and this is a vector field which is transversal to the singular set. We call a singular point of the first kind if this null vector field acting over lambda, over the function, is different to 0. And since the null vector field is transversal to the singular set, we can find another vector field which is tangent to the singular set. So if we have say a cuspidal edge, whoa, terrible. So we have a psi, which is tangent, and a neta, which is the null vector field. And we can consider that pair, which we call an adapted frame, or, well, anyways. And let gamma be a parametrization of the singular curve, and gamma hat will be the image in the frontal of the singular set. So let's go to the geometrical invariants. For example, Martins and Sagi, they studied geometric invariants of cuspidal edges. For example, the singular curvature, the limiting normal curvature, the cuspidal curvature, and the cuspidal directional torsion, which are defined as follows. This singular curvature, if you remember your lessons of classic differential geometry, you might recognize this as similar to the geodesic curvature. In a sense, it is a limiting geodesic curvature in the singular set. And this over here is a normal curvature. Okay, it is the limiting normal curvature. And then these other two, using the adapted frame, the zeta and psi, we can define this cuspidal curvature and this cusp directional torsion. These formulas won't mean anything, but if we draw it, we can understand better these invariants. The singular curvature is the curvature of this cuspidal edge in this sense. The normal curvature is the curvature with respect to the well-defined normal. Okay. The cusp directional torsion is a torsion along the cuspidal edge, and the cuspidal curvature is the wideness of the cuspidal edge. Okay. So these invariants were defined, and we can calculate them for our cuspidal crosscap. Not only the invariants, but their derivatives too. And we will see later why we need the derivatives. This just for you to see that it's in terms of the coefficients of the cuspidal edge normal form. Okay, so we can also consider the curvature and the torsion of the cuspidal edge curve. Okay, and These are given by these formulas over here, but the interesting thing is this, that the curvature of the curve squared is equal to the singular curvature squared plus the normal curvature squared. This is Kendrick's formula in the regular case with the geodesic curvature and the normal curvature. Okay. This was already shown in Martin's and Sagi, but we also have this other relation of the torsion with the singular and normal curvatures and their derivatives, but surprisingly there's also this cusp directional torsion over there. Okay. So these are geometric invariants of the cuspidal edge curve. Now let's study geometric invariants of the rhomboid cusp. So remember we had a rhomboid cusp in a section through the origin. And well, if we take a null vector field which satisfies this, we can define, Honda and Sagi, they define these two numbers over here. This is the bias, called the bias, and this is the second cuspidal curvature. Why? Because if we take a rhomboid cusp, a 2-5 cusp, this number over here measures how it deviates from this form, the bias. So if you have, usually you have t squared t5 for a rhomboid cusp, but we can add here this term over here. And I already wrote it as b, because that number over there is this coefficient, basically. It can be defined for a plain rhomboid cusp or for a rhomboid cuspidal edge. Okay? And the secondary cuspidal curvature is the wideness of the rhomboid cusp. Okay? So, well, yes, what I just explained, the bias and the secondary cuspidal curvature. We calculate them too, and just notice that when b1 of 0 is equal to 0, both of these invariants are 0. And this is because the section that you take through the origin is not generic and contains the tangent line of the double point curve. Okay, so there is no rhomboid cusp. Okay, so we have invariants of cuspidal edge, invariants of rhomboid cusp. Let's go to invariants of the double point curve. First of all, if you have a curve in R3 which is singular, we say that 0 is called of A-type if the second derivative is non-zero. Okay? And it is called of 2-3 type if this vector product is different from 0. In the case of an A-type singular point, Martinez and Sagi define this over here, which is basically like the curvature, but with one order higher of the derivatives. So they call it the singular curvature of a singular curve in space. And we can also define the singular torsion, very similar to the formula of the torsion, but with higher order derivatives. Okay? And also this sigma singular. The interesting thing of these three invariants is that they determine 2-3 type singular space curves up to 4th degree. They determine them up to isometries, obviously. So, okay, we also, in our case, so that's the point. Remember our d tilde? D tilde was a space curve, and it was singular. Actually, it's of 2-3 type. So we can calculate the invariance for that curve. And we have this computation over there. Okay. Also, I mean, you can keep on studying geometric invariants. For example, you can study the limit of the curvature of the double point curve, or the limit of the torsion of the double point curve. But when to stop? When do we know we have enough invariants to know the object? So, I mean, yeah, we could consider also the geodesic curvature, the normal curvature, but there may be relations amongst them. But the main goal is to obtain this theorem. The thing is that if we have two cuspidal crosscups obtained by folding attenuated cuspidal edge, and they have this 16 invariants equal, then there exists a diffeomorphism and an isometry such that this is order 6. What does it mean? That those 16 invariants determine the cuspidal crosscup up to order 5. Okay? So this is when you know you have enough invariants. Notice the interesting part. We have the cuspidal edge invariants and their derivatives. We have the rhomboid cusp invariants and this one over here. This one over here is the singular torsion of this curve. Okay? So to determine the cuspidal crosscup, we are using an invariant of this double point curve in the cuspidal edge. That's what makes it interesting. Good. So this was the first part of the talk. Okay, yeah. This over here has nothing to do with the talk. It's it's a singularity I discovered working in Japan when I was working with Kentaro, and I called it the fugu or blowfish singularity. The fugu, you know, is this fish that if it's not well cooked, you can die or something like that. Because it has more or less a similar shape, and what we have here, this is a cuspidal crosscup. This is the cuspidal edge. Here you have a double point curve. Here you have an ordinary crosscup, another ordinary crosscup, and they're double point curves. So we have a double point curve here, another one here, another one here. This would be a triple point, except for the fact that we have this cuspidal edge. Okay? So it has nothing to do with the talk, but I wanted to share it with you because I think it's a very nice singularity. And it has a cuspidal crosscup, so in a way it is related. Okay. So back to the talk. Well, if you want, enjoy it a bit longer while I drink some water. Okay. So now we want to study flat geometry. We've studied geometric invariants, and now we are going to flat geometry, contact with planes. There are two ways of studying flat geometry. You can either consider your plane or your flat object and consider the different types of deformations of your variety and the different types of contacts with that same flat object. Or you can invert the process and you can consider your fixed variety and study contact with zero fibers of submersions. Okay? And this is the approach that we will use. So we are going to fix the A model of the singular variety, the cuspidal crosscup in our case, and we are going to study the contact with zero fibers of submersions. So we are going to classify submersions under Rx equivalence. I'll just explain this in a moment. So, well, if you are interested in studying height functions, you are going to classify functions. If you want to study contact with lines, you'll study orthogonal projections and classify map germs. But, well, yes, as I said, A equivalence doesn't preserve the flat geometry, so that's why we need to define this Rx group. Who is this Rx group? It's basically the R group, but we are considering only the diffeomorphisms which preserve the variety. Okay? The good thing about this group is that it is a geometric subgroup in the sense of Damon. So we can apply all the singularity theory techniques. We can apply the complete transversals method to classify. We have theorems of finite determinacy. We have theorems of triviality. And we have versal deformations. Okay? So, well, using all these techniques, we obtain a classification of submersions. Any submersion will be Rx equivalent to one of these, but this list is only up to codimension 2. Why only up to codimension 2? Because these submersions are going to describe the singularities of the height functions, and the height functions are in a certain direction, and this direction can only move in an S2, in R3. So we only have two parameters of freedom if we want to versally unfold our singularities. So we only classify up to codimension 2. And well, this is actually codimension 4, but we have two parameter moduli, so we are considering the codimension of the stratum. Okay. So, well, as I said, we want to consider height functions. The thing is, these submersions, if you compose the parametrization of the variety with the submersion, this is the height function. Okay. So basically, we're saying that the singularities of the height function can only be the ones given by these submersions, generically. Okay. So, well, if you consider the family of height functions parameterized by S2, it's just the product, the scalar product, and the contact of M with the plane orthogonal to this direction is measured by the singularities of this function. So if we have a vector like this, notice that in our case, using our parametrization, we'll end up with something like this because we had its corank 1, we had x in the first variable. So this is only singular if and only if v1 is equal to 0, which means that PV contains the tangent direction of the singular variety. And so we have, okay, the geometric criteria, which are the following. If the plane with which we want to measure the contact is transversal to the tangential direction, then we were saying that the height function is not singular. And this is described by the contact of the zero fiber of the first submersion in the list with the model cuspidal crosscut. If the height function along the double point curve, okay, so this is the d hat in this double point curve, this one can have aj singularities for j equals 1, 3, and 5. And these are modeled by the contact of the zero fiber of these submersions with the model cuspidal crosscut. And what are the characterizations or the geometrical interpretations? When is it A1? When is it A3, A5? It is A1 when the plane is not a tangent plane of this curve. So it's not tangent here. It is A3 when it is not the osculating plane and this singular torsion is different to 0. Here is where it gets interesting again. To characterize the singularities of the height function on the cuspidal crosscup, on the double point curve of the cuspidal crosscup, we can characterize it using the torsion of the curve in the cuspidal edge. So you see the relation. There is some, justifies in a way that it is more natural than one would expect to consider this setting. And the A5 singularity if the osculating plane is the osculating plane and that torsion is 0. So here, well, I probably can't see very well these pictures, but this is the A1 case, here the A3, and here the A5. Okay. And if we consider the height function along the cuspidal edge, then it's something like this. We have an A1 singularity or an A2 singularity. And these are modeled by these submersions. And the geometrical interpretations are as follows. A1 singularity when the plane is not the osculating plane of the cuspidal edge. And A2 when the plane is the osculating plane of the cuspidal edge, but the torsion is different to 0. So we are relating the geometrical invariance that we studied with the flat geometry that we are obtaining here. Here you have the pictures, okay, here you see the A1 singularity. If this were a hyperbolic one, you would have the A1 plus. Here I've drawn an A1 minus. And this is the A2 singularity, you can see it there. Okay. And finally, we had this other submersion. And when the plane is the tangent cone, but not the osculating plane of the cuspidal edge, then the contact is described by this submersion over here. Here is where our method is not complete, because if you study the height function associated to this submersion, you will see that the singularity is an A3 plus or minus singularity. Okay? But remember that we were folding the cuspidal edge along a plane. This means that our final cuspidal crosscup is in one hemisphere of the, in one hemisphere, in one semi-plane, semi-space, okay, above the plane. But when we have a minus sign in this submersion, the singularity is an A3 minus. And generically, you could have this. This is generic. This is, you have the cuspidal edge here, and you have the double point curve here. And there is an A3 minus contact. But with our approach, we cannot recover this, because it would always be on one side of the plane. But in any case, at least we have that classification to tell us what we are missing. So it's not bad. Another remark we can do is that Martins and Nuño Ballestero, they proved that the height function in a singular surface, Corank 1, has a sigma 2,2 singularity if and only if the curvature parabola I talked about before is degenerate, that the umbilical curvature is 0, and this I haven't explained and I won't. But the thing is that in our list we only had AK singularities. So that means that this is not generic in our situation. Okay? Having a Corank 2 singularity for the height function is not generic. Okay. So how am I on time? I've got some 5 minutes. Yeah? Oh, okay. So from the point of view of the submersions, there is some geometry which is interesting. We can study the, if we have one of our submersions and we have its deformation with 2 parameters, one of them may be 0 in the case of codimension 1, we consider the composition of this deformation with our parametrization. Okay? That will be F, and H will be when x equals 0. Remember, when x equals 0, what we had was the double point curve. And P when y equals 0, which is the cuspidal edge. Okay? And from the point of view of the submersions, it is interesting to study these discriminants. The DPD, which is points in R3, or parameters, and the value of the function, such that the partials are equal to 0. Another interesting set is the DPC, which is when the partial of h with respect to y is 0. And another one is the DCE, which is when the partial of p is equal to 0. Why are these letters? They are obviously not arbitrary. PD, DPD means, well, this D is for discriminant, PD is for proper dual, which I'll explain in a moment. DPC is double point curve, and C is cuspidal edge. And well, if you have 2 deformations which are PR plus X equivalent, then their associated discriminants will be diffeomorphic. Okay, so this is, well, so we can study these sets for our submersions, because basically these sets are the duals. If the plane contains the tangent direction of M, but is not the tangent cone, then the DPD and the DCE are equal, and they describe the dual of this cuspidal edge. Okay. If the plane is the tangent cone, then the DPD consists of 2 components, one which is the DCE, the dual of the cuspidal edge, and the other one is what we call the proper dual, which is the surface consisting of the tangent planes to M away from points on the cuspidal edge, together with the tangent cones at the points of the cuspidal edge. Okay, so it's the proper dual. We have the dual of the cuspidal edge and the proper dual. And the DPC is the dual of the double point curve. If the plane is transversal to the limit tangent vector of the double point curve, then the DPC consists of just 1 plane component. But if the plane contains the limiting tangent vector of the double point curve, then the DPC consists of 2 components, one which is a plane. So it is interesting to study these discriminants. For the first interesting submersions, we have that the DPD and the DCE are empty, and the dual of the double point curve has 2 components. One in which is a plane. This is for k equals 2, and this is for k equals 3. For k equals 2, we have this plane and this other semi-plane. And here, it's difficult to see, but this is a cuspidal edge. It's a cuspidal edge that ends here. And here, we have just a plane, semi-plane. This you might recognize as BK singularities or boundary. and they appear in other different contexts. For these submersions over here, we have that the proper dual and the cuspidal edge and the cuspidal edge dual are equal, and these are the pictures. So this is the dual of the double point curve, and this is the other one. And here you have a cuspidal edge, which is inflectional in the contact with the plane. Okay. And finally, for this other singularity, we have an interesting situation. This is the dual of the double point curve, which has two components. And here, the dual of the cuspidal edge is the yellow component, and the blue component is the dual, the proper dual. So, no, upside down, sorry. The proper dual is the yellow component, and the dual of the cuspidal edge, in this case, is a cuspidal crosscup. Okay, so the dual is again a cuspidal crosscup, and we have here the double point curve, and the cuspidal edge is contained in this plane. Same here, the cuspidal edge is contained in this plane. So, well, that is more or less the way in which we approach a singular surface and try to study generic geometry. We try to obtain the normal form, which in our case we avoided by folding the cuspidal edge. We study geometric invariants. We relate those geometric invariants to the normal form that we have in each case, and then study flat geometry and characterize the singularities of the height functions with we study flat geometry and we characterize the singularities of the height functions with the geometric invariants that we had obtained. And with this, like, you can close a circle about generic geometry of that singular variety, which in our case was the cuspidal crosscup. And basically that's it. So thank you very much, and happy birthday, Federico.
Are there questions or comments?
Just first comment, the Raúl class is A-class unit 5 jet, but if you want to teach geometry, the work of Raúl, you have to go to the 6th jet. So for example, T5 to 6.
No, the generic Ramford cusp is this one over here. T4 plus T5. No, you don't have to go to T6. This is the generic. We have it in our paper too. Yeah. But
The second thing, if you take the cuspid edge, you have the elliptic parabolic, there is classification of cuspid edges, yes?
yes.
Does this reflect if you take the elliptic one and you fold it, you get different types? Or?
Well, first of all, we don't have a definition of elliptic cuspidal crosscup or parabolic cuspidal crosscup. Obviously, we could imagine one, but the thing is, remember, when we fold, we'll have everything in the upper semiplane. So yes, you can have parabolic and elliptic cases, but the truth is, I haven't thought about it. Yeah, but well, yeah, it could be interesting to see.
Also, when you fold, you have a choice of the folding plane, as long as it's not.
As long as it's transversal to the cuspidal edge, yeah.
Does this give you different geometry?
No, I mean, because we used a generic normal form for the cuspidal edge, and we took a plane that was transversal to it. So this generic normal form gives you all the possibilities of the cuspidal edge.
Because one way of being maybe from the up and down minus if you take family, you go from one to another.
I mean, anything generic that you can obtain from our approach is contained in whichever plane you use that is transversal. Because if you because the normal form is already giving you all that freedom of genericity of the cuspidal edge. So if you want to choose another plane, change the coefficients of the normal form, and you will have an equivalent situation.